Okay, here's problem number 7 from the video review. I talked about in class giving you another example of this because I kind of got a little turned around on the inequalities when we were working through this problem. So let's go through it. In this particular case, what I want is I want to know what the regions in the S-plane are for an ideal second-order system with certain performance characteristics. So we should meet or exceed the following specifications: a rise time of 2 seconds or less and a settling time of 2.8 seconds or less. And we should have a maximum overshoot of at most 25%. Alright, so here's where I got it turned around before. The best way to approach this is to write down the parameters. Okay, so I want TR to be less than 2. Okay, well, TR, what is the rise time for an ideal second order system? Well, it's 1.8 over omega n to be less than 2. Alright, so I can solve this inequality and show that omega n has to be bigger than 1.8 over 2. Alright, so 1.8 over 2 is, I calculate that. Oh, that's embarrassing. 0.9. Of course, it's 0.9. All right. So I know that omega n has to be bigger than 0.9. All right. And then I have a picture in my head about what omega n means. I'll draw that in just a second. Okay, now we do the same thing for settling time. The settling time has to be less than 2.8 seconds. The formula for settling time is 4.6 over sigma. So this gives you a bound on the real part of your S-domain roots. So that has to be less than 2.8. So sigma, okay, has to be greater than, let's see, 4.6 over 2.8. Okay, so 4.6 over 2.8 is 1.6429. So let's call it 1.65. All right. Then the last thing we need is we need the damping ratio zeta, and we can get that from a formula. The formula is square root of the natural log squared. So you calculate the natural log, then you square it, of MP, pi squared plus natural log squared MP. Alright, so we know that MP is 25%, or in this formula, 0.25. So I simply plug in, and you end up with zeta equal to 0.46. Okay, rounding up a little bit. Then, to sketch the region, I need to know theta. All right, I'll show you the picture here in a second. It's the arc sign in degrees. So, in MATLAB, there's a command called a sin d that gives you the answer back in degrees of 0.46. And when I do that, I get theta to be 27.1 degrees. Okay, so what I know is my theta has to give me an overshoot of less than 25%, and so theta can be no larger than 27.1 degrees. Okay, so here's the pictures. When you put all this together, we have the S-plane. Okay, omega n is a radius. You know, it's a circle of radius omega n. So here's 1. So omega n has this radius of 0.9. So just kind of eyeballing that. So I know omega n has to be outside of that. All right. And then I look at sigma. Sigma is the real part. Sigma is 1.65. Okay, so here's 1. This would be 2. So 1.65 would be somewhere in here. And I know that the real part of the S-domain poles has to be to the left of that line. Okay, so here's the line sigma, and here's the radius omega n. Okay, and then finally we sketch in the angle theta. So theta is about 30 degrees, so we would draw it about right here and here. Okay. Well, that's not the right spot. Sorry. It's 30 degrees from the vertical. All right, so we're looking at about here. And here. Okay, so this is 27.1 degrees. All right, and so we're looking at an intersection of all these regions. So let me sketch the regions in. We know that omega n forces this blue region. That's the constraint on omega n. Okay, then, I'm sorry, it goes even further. The blue region. Anything right half plane and in the blue meets the omega n constraint. Okay. Then the sigma constraint on the settling time, we'll sketch that in red. Okay, that's anything, you know, to the left of this line. Anything back in here. Okay, and then the angle, make that yellow or gold. The overshoot requirement requires us to be within this angle. Okay, so we intersect all those things together, and our point of intersection is this nasty looking rust color in here. Okay, so all the poles have to be, you know, over in this region for the two poles in order to